Let's get started for today's session. My name is Mihir Thakkar and I am the founder and instructor at Kodiroku. What we try to do is arrange hands-on workshops like these where students can come and talk to our instructors and get their questions answered in real time rather than watching a 3-year-old YouTube video which might have outdated content, and as well as the questions that you might not be able to get answers to them directly. But what we try to do is have these live sessions so that if you have any questions, you can ask your instructor right at that point, get your doubts cleared. And also, we try to focus a lot on the hands on aspect of it. Most of our sessions, we want to make sure that once you complete our workshop, you are able to write something or create something on your own, a working software that you could show to your friends or maybe even in your job interviews. That's how we are different from others. In today's workshop, we are going to learn about computer vision. And before even now, I try to tell you what computer vision is, I want to get a sense of what you guys know about computer vision, what you might have heard about it. When I say computer vision, what's the first thing that come to your mind? Yep, how a computer sees. That's the literal translation. And that is it. That is what we are trying to do. We are trying to give our computers the ability to be able to actually see and understand things around them. And if you think about it, until few years back, this was not possible. We were doing it in a very naive way, but our computers, which were supposed to be the most powerful tools that we had, were practically blind. Like they couldn't understand and see the things around them. And that's why this field of computer vision or this area of research is so critical and so important, because our computers are the best tools that we have. And if they are not aware of their surroundings, let's say if you have a robot in your home, but if it can't see things around it, it's not that useful. If we want to live in that futuristic, something like a Tom Cruise future movie, and if you see that there are robots going around, it's highly likely that you would want them to have that sense of vision in them. We advance the field of computer vision because unless our computers are most powerful tools that we as humans have, and it's critical for us to get to the next technology level. It's important that our computers can see and understand things around them as well. Let's see what we are going to see in today's session. Today we are going to see what is computer vision at a very high level. You guys already get a sense of what computer vision is from the word itself, but we are going to see specifically what are the areas, what are the technology fields, what computer vision covers. And then some of you already know this, but still, as an encouragement or as a motivation, I would want you to show you what are some great things that you could do with computer vision, and thus you should know why is it so important for you to learn it as well. And everything is great. You love computer vision, you see that it's the future. Most jobs in the future or programs or softwares that gonna build are gonna need some sort of computer vision aspect to it. Everything is great, but how you should go about learning it? Sometimes we kind of get lost in the abundance of resource which is available on internet, and sometimes we can't figure out. I see a whole bunch of resources there, I see a lot of books, I see a lot of videos, but no one is telling me that sequence. Where should I start and where should I end? I don't see the entire road in front of me, and how the hell I'm supposed to go from point A to point B if I don't know what that road looks like? My idea over here is to give you a sort of map that you could navigate through, and hopefully that is going to help you select a few domains, because computer vision is a broad field of research. People spend like 20-30 years working on it, and it's going to be difficult for you to pick up something in next 1 or 2 years so that you are good enough to be dangerous. That's what I tell most of folks who talk to me. You don't necessarily need to know everything about a subject, but you want to know enough to be dangerous in that field, so that if someone puts you on that project, you can quickly pick it up and take it from there. And I'm not sure if you noticed that thing about our workshops as well. What I'm trying to do is cover a broad range of topics. We have workshops from machine learning, we do workshops on building web apps with Python, We also did one on JavaScript and data visualization. What I'm trying to do is now cover a broad range of topics so that you know enough in a domain which might spark your interest. And once you have that interest, you can go ahead and learn more about it, go deeper into it. But I want to make sure that you have that platform, the base strong and ready over there on which you can build on top of it. And then we're gonna see some basics of image processing as well. And I'll show you how image processing fits in with computer vision as a field. How is it different or how is it similar to computer vision? And eventually, we just don't want to study some theory, but we want to get hands-on on our Python, and we'll be using a library called OpenCV. I don't have a lot of slides today explaining things about OpenCV, but let me just give you a background on how I got introduced to computer vision or OpenCV. So I was trying a project. I was doing a project more than 8 years ago, I guess, on building a gesture recognition algorithm using. We didn't decide a tool, but we eventually ended up using C++. At that time, I was looking for libraries on what could be some possible ways to implement this algorithm on recognizing hand gestures. And that's when I came across OpenCV, which is from Willow Garage. If you look them up, they are quite a popular open source resource or community or a company. And the things that they produce are really good. They are very high caliber. I said that, what, if this company is doing it, there must be something to it. At that time, it was not that popular. And now it has gained a lot of traction. It is one of the most popular image processing, computer vision, and to some extent, machine learning library as well. There are some functions that you can use to help build your machine learning models as well. That's where OpenCV comes in. It's a very powerful tool. We don't want to redo the work that they have already done in trying to manipulate basic image functions. What we're going to do is use a lot of OpenCV tools. And once we understand how to use those tools at a higher level, we can always dig in and investigate further on how those tools work. But at this point, we don't want to really reinvent the wheel and try to implement what OpenCV already does it for us. We want to make sure that we are solving problems which have real impact and not things which are already solved. There are a lot of functions, a lot of algorithms which OpenCV has already implemented. Let's go ahead. What we're going to try to do is, even though it might look more like magic right now, in terms of you're writing a line of code and it's doing everything, but once you understand at that abstraction level, it's much easier to go one level deeper and understand how that algorithm works. That gives you a broad sense of what our session today is going to look like. Let's do a visual rapid fire. I'm going to show you few images and I want you to describe what do you see. But I'm going to give all of you only, let's say, 5 to 6 seconds per image. And I'm going to quickly browse through it. Here we go. Okay, celebration. That one was good. Most of you got a lot of those things right. And the thing that you did right now over there, it has been one of the most difficult things that we have been trying our computers to teach. How do you understand what's going on in the scene? If you look at these images, it's not straightforward. It's not very easy. There is a lot of background information. In this case, it's a blurry image. You can hardly see. But just by looking at hands, you could make out that it was party or it was a concert like this. But trying to teach a computer that this is not someone trying to say bye to someone, but this is people who are waving their hand in a concert, it's a pretty difficult thing to do. Think about it. Even this one, it's not just the shot is taken from up, it's a top view of someone drinking coffee. And again, it's only in recent days The advancements that we have made in deep neural networks, which has been possible, because of which it has been possible, so that if I give this image to Google right now, it is most likely going to come with relevant tags today. This was not possible 2 to 3 years back, and that has only been possible because of our advancement in machine learning and computer vision. Think about it. Even if you give this to a 2 or 3 year child, they might be able to tell you that this is a dog or this is a cell phone. But trying to teach our computers, it has been very difficult. And at this point, we are at a stage of maybe a 3 or 5 year old kid. That's where the state of computer vision and machine learning is. That's the ability that our computers have, is similar to about someone who is a 3 to 5 year old kid. As you see, there is no lot of room for improvement. There is a lot of work that needs to be still done to be able to reach to not only be able to understand or match with human abilities, but even surpass that. It's really critical. I don't know if you heard about it, but Google's voice recognition engine, they have actually surpassed to the ability of humans as well. In voice recognition field, we have advanced a lot, but when it comes to computer vision, we are still equivalent to someone as old as 4 or 5 year old. There is a lot of room for improvement over there. Let me tell you what are the three basic areas that computer vision tries to cover. When we talk about computer vision, we are talking about what is inside the scene. We are trying to understand, just like you guys did with the tags over there, you are trying to tell what's in the scene. You are trying to tell me that it's a concert, it's a cell phone, some people are busy. You were trying to get the context from the image. And that is one of the objectives of computer vision, or the field of computer vision is trying to understand what's in the scene. And then once you know what is in it, you might also sometimes want to know where inside the image it is specifically. Sometimes you might know that you are always looking for an apple in the image, but now you want to count how many apples are there, and you also want to know where in the image those apples are, so that maybe you could do something with it. Or let's say it's an automatic shooting system. Very bad example, but let's say if you want to shoot someone, you would want to identify where in the image that person is. And then you want to know how to manipulate objects or move around the scene as well. In many applications, specifically in robotics, what you want to do is navigate, let's say, from point A to point B. And even though it might seem a very trivial task for us as humans, trying to teach a robot to go from point A to point B is a very challenging problem. First of all, the robot needs to plan its path. There is a whole domain or field of research on path planning itself, on what kind of actions or what are the steps that a robot needs to take for it to go from point A to point B. Because in real world, it's not that straightforward. There might be some differences in the actions taken by robot and actual actions which are performed by the motors or the gears. So you need to take into account all of that scenarios before you do the path planning. The computer vision field also tries to cover those things, not only in terms of image processing or not only being able to understand what to do and where is it, but also tries to cover the domains wherein it is trying to manipulate the real world around it. Instead of me just talking about these applications, let me just go ahead and show a video to you. Let me go ahead and play it. All right, so pretty cool, right? I thought that was pretty inspirational and just wanted to show that to you guys as well, because a lot of things that I spoke about in past few minutes, you actually saw that in action when I was talking about path planning. So we saw a robot which was going around, and few other applications that you saw were detecting people, detecting faces. We also saw drones. The drone was trying to pick a ball over there. Not only it had to track where the ball was, and as you see, it was trying to recalibrate itself and adjust itself to the position of the ball. Not only do that, but you also want to come up with a set of actions which will enable you to pick that ball. The computer vision field is broad in that sense that it is not just limited to doing the processing of the videos and the images, but also you want to understand what's in the scene, where is it, and now how do you go about manipulating the real world. Hope that makes sense to you guys, and I'm not going to talk more about applications. I think that it's clear enough from the video on broad range of things that you could do with computer vision. All that was good, pretty fascinating, inspirational, but there are some real world challenges in building a computer vision system, and that's the reason you don't see every other company working in that space. It's not that easy. It's a difficult to solve problem, but I wouldn't say it's difficult to learn for you. The reason why I say that is the amount of tools that are available these days and the resources that you have is pretty phenomenal. And what you could do is get started at a very basic level and reach to a point where you are able to build some basic applications like those in about 6 months or so. I would say that if you spend about 6 months studying computer vision, you would be most likely making a basic version of most of those applications that you just saw. What are some real world challenges in building a computer vision system? Well, the real world data is very noisy. And as you might imagine, when a person is walking, just like you saw in that video, it's not only that person, but you would have some background cars, you would have some trees, you would have some other objects which are in that scene. The data that you have might also be gone through several computer networks. They might have several noise factors in them, or you could have some Gaussian noise, you could have some other types of noise in there. The real world data is very noisy, and it's not very easy to separate out things which are of our interest from those which are not of our interest. And then you have this ongoing problem of the scale, orientation, and lighting variations. All the images that you saw over there, let's say if you want to do the tracking of the ball, just like we saw on the drone which was trying to track the ball, again, it might work for some lighting conditions and for some orientations, and it might not work for some others. If you put that drone in the evening, it might not work, and in real world applications you can't really have that. For proof of concepts, it's okay, but if you tell an army commander that no, this drone can navigate only in the morning, but it won't navigate in the evenings, that army commander is not going to take or no buy your drone. It's easy to make some prototypes, but as you go in real world and start doing some real world applications, you see all these challenges in terms of the lighting variations, the scale variants, and the orientations as well. That's difficult to solve. And there is always a lack of data and annotated data. Even though we have several libraries out there, open source image collections that you could use to build your machine learning models and do your image processing applications, there is always going to be lack of data in the field that you try to come up with for problems which have been solved. I'll give you an example. One of the problems now you could take that as solved is called as optical character recognition, or OCR, wherein you try to read the letters from a picture which was might have been taken several years back. Let's say if you want to digitize all the newspapers which were from 1960s to 1980s, you have scanned copies of those newspapers. You don't have the word files for those newspapers. Now how do you take that data and digitize it? That's a optical character recognition problem, and I would say that that has been solved to a good extent. For problems like those, you will get a lot of data sets. So you will get a lot of digits, a lot of variations of how the letter A or the B could be written in English language. But if you try going to the fields where the problems which are not have been solved, for things like how to detect if a tumor is deadly or benign, let's say how to track the joints of a human posture, those are the problems which are not have been solved yet. And for those, you won't get those data sets very easily. You will have to create your own data sets. And in machine learning applications, we are building a data sets of at least thousands and 10,000 images, and for each gesture or each posture that you have. So it becomes very challenging for you to create this data set if you don't have that to start with. Those are some challenges that you have in building a computer vision system. And before we go to our hands-on part for today, I also want to make sure that you guys understand some basics around image and image processing. If we were doing this workshop, maybe let's say 15, 20 years ago, I won't be doing it. But let's say if hypothetically, if this workshop was organized 15, 20 years ago, you guys might not know what a pixel was, right? But in today's digital world, we have our smartphone cameras, and it's become so mundane and it's so become part of our life that everyone knows what a pixel of an image is. But let me just go over it, and let me just make sure that you guys understand some details about it as well. Let's say we have an image like this. It's a giraffe and it's in a grayscale image. So essentially, there are three main types of images or categories of images that you would come across. The first one is the color image. If you take a picture from a smartphone, you'll get a color image out of it. But what you could do is now convert this color image that you have from your phone to a grayscale image. And the image that you're seeing on your screen is a grayscale image, wherein each pixel can have, let me just show you what a pixel is. If you go on and keep zooming in on this image, at one point you will come across this square over here, which will look something like this. And if you zoom in further, you will see that each square like this is also made up of tiny smaller pixels. And in this case, this is how the extra zoomed in version of this image looks like. It's just a collection of dots which is making up the entire image. And over here we are seeing that this is a grayscale image. And how do I know about that? Because I can see in the values of these pixels over here that each pixel is ranging from around 0 to 255. For a grayscale image, each pixel value in terms of integer could have the range from 0 to 255. That is a total of 256 levels of grays that they have over there. This is how a grayscale image looks like, and this is how it is structured. You keep zooming in on an image and you will reach to a point where you can't break it anymore. What you want to do is, for digital images at least, you will reach to a point where you can't divide them anymore. The region that you have is the pixel of that image, and each pixel in a grayscale image can range from 0 to 255. The next thing that I want to tell you is, when we are talking about image processing and computer vision, we generally have our axes set up like this, which is a little bit different than what we traditionally do in a graph. Our x-axis is still horizontal, y-axis is still vertical, but we take the top left corner as the origin. This pixel, this 205 over here, let me make sure that you see my pointer. This 205 over here, this is the first pixel that we're going to consider, or the 0th coordinate, 0, 0. This is our origin for us. So this is always going to be 0, 0, and the x-axis will increase in this direction and the y-axis will increase in this direction. This will go from 0, 0 to the width of this image, 0, because y is still 0. And this will go from the 0, 0 to the 0, height of this image. The total height of the image is h. It will go from 0 to h. When we are working with images, this is how we will consider this image pixels to be numbered from. It's essentially a matrix. It's a matrix or a table. And what we are saying is the first cell in this location, in this matrix, is the 0, 0 location. And that's how you would do in matrices as well. when you treat images like matrices, it becomes easy to you to know do those computation. A lot of times you are going to see that operations that we do on images are going to be similar to the matrices operations that you might have studied in your basic math class. And then you have color images. This one was a grayscale image, but then you could also have a color image like this, wherein the entire image is broken down into three layers. So here we have the three planes for R, G, and B, and each plane over here, and this is just a plot of the depth of that image. Here they have spikes for the green levels, they are the spikes for the red levels, and these are the blue levels. And if you plot a histogram out of that, this is how it's going to look, the depth of the image. This is what we said about color images. For color images, we know that the entire image is broken down into three channels. So we have three planes similar to what you would have for a grayscale image. Now, instead of just having the values from 0 to 255, each plane will have the values from 0 to 255. And based on the combination of those three planes, the effect, the end result that you're going to see is the color image that you see from your smartphones or any other color camera that you have. Those were a few basic concepts that I wanted to make sure that everyone understands before we go to our hands-on part. And just one thing that I wanted to tell you guys is about the fields which are part of computer vision. And even though I have spoken briefly about them, let me just go ahead and show you the stages of how the image gets processed. Essentially, what we want to do is break this bigger problem that we have is how do I learn computer vision? That's a big problem. And now let's break it down into smaller parts. What we're going to say is, okay, what does computer vision comprise of? And once we know what are the smaller divisions in computer vision itself, now what we could do is learn concepts from each of those phases. And then now we can think about mastering computer vision. At first, you have the image or the video capture. To do anything with the real world in terms of visually being able to manipulate or understand it, you have to first capture that image, capture that video. And while you are doing that, some concepts that are going to come into play, or some concepts, similar concepts that you should be aware of, are things like sampling, quantization, and things that you might have studied in your basic digital signal processing class. Even some people might have taken up a computer image processing class. Those are the things that you would want to learn about, and a lot of us have already seen our curriculum in engineering or basic science as well covers these concepts of sampling and quantization. You want to make sure that you understand all of those. And when someone tells you something about aspect ratio, you know what an aspect ratio is. Again, this is only possible because images and videos have become so much part of our daily lives that when someone tells me about aspect ratio, it's most likely that you're gonna know about it. Then what you want to do is you want to do a lot of filtering on it, because as I said, the real world data is noisy. You also want to make sure that sometimes you pre-process it so that it becomes more suitable in the future stages of the pipeline. There are some pre-processing algorithms and filtering techniques that you would want to learn about. And once you have pre-processed your image, the next thing that you want to do is extract some features out of it. These are the same features that we spoke about in our machine learning class as well, wherein you are trying to figure out what are the shape, what is the color, what are the features which are most going to be likely impacting the decision of your machine learning problem, or what are the parameters that you should take into consider while trying to solve your problem. These are the same features that we're talking about, and there are some different methods on how you go about extracting your features. For example, you could do a contour detection, you could do some edge detections, or there are some transforms such as principal component analysis, which is PCA, which you could use to reduce the dimensionality of that image and take few principal components as your primary features. And once you have extracted those features, the next thing that you want to do is build your supervised or unsupervised learning models. And that's where the field of machine learning comes in. And by the way, the first three stages that I spoke about, this is the entire image processing pipeline. When we talk about first three phases over here, that is how image processing fits in the world of computer vision. When someone tells you or asks you what's the difference between computer image processing and maybe computer vision, that's what I want you guys to tell them is the image processing is nothing but a part of the whole computer vision pipeline. For image processing, you would have an input image and the output will be an image as well. So over here, you have some sort of edge detected image, or you're still working with pixels. We said that once you extract your features, the next thing that you want to do is build your machine learning models out of it. That's where the machine learning aspect is fitting in. And the next thing that we spoke about is how does image processing fits in the world of computer vision. And when someone asks you how is image processing different than computer vision, I want you guys to tell them is for an image processing pipeline, the input is an image and the output is also an image. But in the world of computer vision, what we're trying to do is trying to understand the world around us. So we are trying to do three things that we spoke about. We want to know what's in the image. The next thing that we want to know is where is it? And the third thing that we want to know is once you know what is it and where is it, you also want to know how do I manipulate it? How do I go about acting on that real world? And that's where the machine learning model also comes in the first two parts, where it is trying to understand what is it in the image and where is it. That's how you will use the machine learning model. And then the final part is how do I go about manipulating the real world object? That's where the real world manipulation aspect comes in. So you want to learn or study about things like localization, object tracking, path planning. And these are more of I would say mechatronics or robotics problems. This is how the entire pipeline is set up as such. I wanted you guys to give you a brief at a very broad level. I wanted to cut them up and wanted to give you some examples of concepts which are in those fields. Again, this can't be comprehensive because there is so much to learn in it and there is so much that you could go over. But what you could do now at least is you know what are the stages in the computer vision pipeline. And maybe you know what, you might not be interested in the first three phases over here. You might think that this is a boring part. You just take image and you work with it. You might say, you know what, I'm just going to stick with my machine learning, irrespective of whether it's an image or a voice. I don't care. I just want to work with machine learning models and I want to build some machine learning algorithms. So fine, then you can stick with that. But let's say someone wants to do an application end to end. They are interested in augmented reality. They are interested in being able to build some virtual worlds from the real world images. In those cases, you want to be able to understand the entire pipeline, and just learning machine learning won't help you at that point. Or even for robotics, if you want to be able to build a self-driving car, well, in that case, just learning machine learning itself is not enough. You want to understand how the sensors work. You also want to understand how the LiDAR might be functioning. What's the sampling rate over there? How would you go about filtering the LiDAR data? How would you go about extracting those features, the cars, the pedestrians from that image, and so on? Let's get into the hands-on part. I'm hoping that everyone has downloaded OpenCV using the pip package manager that I have given you. Go ahead and open your Sublime text editor or any other editor that you are comfortable working with on Python. Go ahead and open the Sublime text editor. Let's go ahead and write a very simple program. And what I want you to do is open your Sublime text editor, go to File, Save As, and save your file in the library or the place where you want to work in. So I'm going to work in this computer vision folder over here. What I'm going to do is, let's say I'm going to write a very basic program. So let's just say hello cv.py. I created a simple file over here and I saved it, and I'm going to say import cv2, which is the first command that I had asked you to test out as well, that if you have your OpenCV installed, I want you to import cv2 and try to run that. Save it and build it. As you see, my program executed and it ran without any errors. Run it using Control B, build it using Control B. Next, what you want to do is, let's just read an image and display it on a screen, because that's similar to hello world that you would do. In terms of computer vision, what you want to do is be able to read and write videos all the time, or read and write images.
You will be taking images, processing it, and then trying to understand it. The first thing that we want to do is let's learn to read an image in our program. The way we are going to do it is, what I want you to do is take any image that you might have on your computer, or you could just go to Google Image and just pick any other image from there and place it inside your folder where you have saved this file. I am inside this folder called computer vision over here. I have this image called image.jpg over here in the same folder. Go ahead and paste an image inside your folder. Just take it from Google Images or any other image that you already have on your computer. Place it inside your computer vision folder, and I would prefer that you rename it to image.jpg or image.png or whatever extension it is. Make sure that you rename it to a simple file name. Otherwise, you're going to make some silly mistakes when we write the program. Paste that image over here in the folder, which is same as your hello_cv.py in my case, which is, so this is the program I'm writing, hello_cv.py. Let me just clear this. So what I'm going to do is take everything else, move it to an old folder so that you guys can see it properly. What I did was I had an image called image.jpg, and I'm going to paste it inside the folder where I'm working in. I'm over here. I have my program hello_cv.py, and this is the image that I pasted over here, image.jpg. And now our task is to open this image inside of our Python program. Let's try to open this in our Python program. So what we're going to say is input image is equal to, we are going to use the OpenCV. What we are saying is input image is equal to cv2 dot imread. This is saying image read. I'm going to say image.jpg or whatever your file name is. Make sure you don't make any silly mistakes over here. This is what we're going to say. And then let's just show it on our screen. So to show that, we're going to say cv2.imshow. Let's just give it any name. This is just the name of the window. We're just going to say image, or let's say this is my image, and I'm going to say input image. Save it. If you are done with this part, try to go ahead and build it. What happens? Go ahead and run it and see what happens. I tried running it. Something happened there, but I still didn't see the image. The image shows and disappears. You saw something coming up, but it then went away. Have you guys heard of getch in C? If you guys might have heard of getch, that is what happening over here. It's running it, but we are not waiting enough for it to show up. What we are going to do is a similar to getch, an equivalent of that. What we want to say our program is wait, and don't go away from here. Wait at this point. I want to see the image. What we want to say is cv2.wait 0. And then we want to say cv2.destroy all windows. And that's the reason I'm not going to cover a whole lot of things today, because a lot of this is going to look like magic to you. And how am I getting these function names? How am I supposed to know that you should write this? But again, what I'm going to show you later is how will you go about looking up for these lines or these resources online. But a lot of this is standard way. It's just the way you would set up any image processing program that you have. The cv2 is the name of the library that we are using. We'll have to use it. Otherwise, we'll have to import all these functions one by one over here. So you would have to say import cv2.wait key, import cv2.destroy all windows. So we don't want to do that. We don't want to write those many import statements. But all these functions are part of that library, and thus we'll have to use the cv2 name. If you don't like having cv2 over here, what you could also say is import cv as, I should actually say cv2. I don't know how did I mess it up. Make sure you are saying import cv2 over here. And you could also say import cv2 as cv. If you don't want to use cv2 every time, you could say import cv2 as cv. Then you can change all of these to cvs. But I don't want to confuse everyone. So stick to this. Use import cv2, and then everything else will be cv2. Let's try to run this now. And let's see if we have our image there. I made a silly mistake over here. This K is in camel caps. As we see, we have our image that I had on my computer displayed over here. This was very basic image reading. We were able to read something from our computer and we were able to get this inside our program. The next thing that I want you to do is, in a lot of times, we don't want this color information. Let's say if I'm trying to analyze what's happening in this scene, or if there are any people in this scene or not, in that case, the color information is not going to really help me. All it's going to do is try to distract my machine learning algorithm. A lot of times what you're going to see is we are going to use a grayscale image rather than using a color image. Can someone tell me or think about, because if I tell you everything, you're not going to remember it forever. But if you stress your mind and think about, why would you use a grayscale image besides what I just said? Sometimes the color information is not really useful. Besides that, what could be some advantages of just having a grayscale image? Kiranjit says less information to parse or process. Partha also says that can be faster. Definitely. Again, over there we have 3 planes, right, that you are working with. So if you discard those 3 planes, eventually now you're just working with 1 plane or 1 set of zeros to 255. You are essentially reducing your data to 1/3. That's significant speed up. And a lot of times when you process this, if it's just a single image, it won't matter that much. With the computing power that we have right now on our computers, it's nothing for it. But when you do real-time video processing, that's when things might change, because you want to process frames at the rate of maybe 20-30 frames a second. And if you are doing a frequency of about 20-30 hertz, you need to consider how much data you are trying to process and what algorithms you are using. Let's try to read this image. Instead of reading the color image, what we're going to do is read it in black and white image. And again, then we also try to save it to our computer. Sorry, my bad, not a black and white image, but we are going to convert it to a grayscale image and then save it to a computer. A black and white image will have only 2 values, 0 and 1 for every pixel. It's either 0 or 1, but a grayscale image will have values from 0 to 255 for every pixel. That's how they are different. Let's go ahead and read this image in grayscale mode. And to do that, what we're going to do is, instead of just saying cv2.imread, what we could do is add another parameter over here. So we could say comma 0 over here. And if we do that, it's going to read the image in a grayscale image. Before we write and save it to our computer, let's just see how that looks like. I'm going to run it again. And as you see now, instead of the color image, I'm seeing a grayscale image, grayscale version of it. And the color information is gone away now. No one is telling you to use 0 to 255. If in your application, you think that the values from only 0 to 10 matter to me, you can convert your image to have values only from 0 to 10. No one is asking you to use 0 to 255, but can everyone else think about why would just a number like 255? Where is this number 255 coming in? With 8 bits, you could store 256 values essentially from 0 to 255. Given that you are taking that byte of memory over there, now it makes sense to count in those multiples essentially. I'm not sure if that answered your question, but there is nothing stopping you from converting the levels. Let's say you are doing an embedded system and you would want to preserve memory. You don't have that much of memory, and you would say that I just want to store all the image pixels in only 100 kilobytes, this large image. Now you can't store that many pixels, those many values. So you would just downscale this and you will lose some visual information over there. But you could say that, you know what, it's fine for my application. I don't need those many values. Yeah, so there is definitely that trade-off. You lose some visual information, but if that doesn't matter in your application, it's fine. Let's go ahead and save this image as well on our computer. We'll see how to save that. We can go over here and let's save this image. Try to go ahead, and this is something that we do in a lot of our workshops. For those who are new, once you go out of here, I want to make sure that you are able to find things by yourself. And that's why I let you guys search for things on Google. Why don't you go ahead, search on Google, what is the function name that you would use to save an image on the screen using OpenCV and Python, of course. All right, so here's how I would go about searching that. I would go over here and say, first of all, we are working with OpenCV. So we'll say OpenCV, then I'm going to say Python, and then I'm going to say save image to file. What I see over here is in the first link itself, I'm seeing that there is an option to display the image. And then again, this is something that we already did. Then they also have an option to show the window and write an image using cv2.imwrite. I'm just gonna copy this thing from here and take it to my file over here, paste it, and let's replace the names. This seems like the file name. So I want to say black and white image.jpg because I'm using a JPEG file over there. And the name of my input image is input image. I'm gonna save it and then let's run this. It looks okay. Close this. Let's go to the folder where we were working it. We saved it over here, right over here, and we got this image. Some of you might be thinking, oh, you know what, this is more of image processing and not just computer vision, right? I'm more interested in the machine learning aspects or the real world manipulation. But again, to do those things, this is the first stage of our pipeline. As you saw over here, the stages that we saw, this is where the image processing is coming in, from image capture to pre-processing to feature extraction. Today, my goal is to try to cover some basics around these concepts. And then once you have a good understanding of these, then you can think about going in these two stages as well. And in our machine learning class, we are already learning how to build machine learning models using some simple algorithms over there as well. Maybe we'll try to relate both of these classes as well at some point. This was good, right? We were able to write something to the image, but a lot of times we also need to do some manipulations on the image itself, not just converting it from color to grayscale, but also sometimes you want to draw some rectangles around it. And the reason you might want that is, let's say if you're doing a face detection. So if I'm doing a face detection algorithm, I want to show where on the image or where in the video that person is. So I want to draw a rectangle around his face. In those cases, drawing something on the image itself is very handy or very useful. I would want you to try and search for a function which will allow us to draw a rectangle on our original image. Go ahead and search for a function which will allow us to draw the rectangle on the image that the input image that we have, and try to look for the documentation of the function and try to understand what the parameters of those functions are. All right, this is how I would go about searching it. Let's say I want to search for OpenCV, Python, draw rectangle. The first link over here says drawing functions in OpenCV. Sounds familiar. This is what we want to do. We see that we could draw a line, circle, rectangle, cv2.rectangle over there. Looks good, looks something that we are interested in working with. Let's go to the rectangle. Here it is. So it says draw rectangle, and these are some parameters. Instead of just trying to copy paste things, what you also want to do is make sure that you understand what are the parameters of these functions before just doing a trial and error. Sometimes what I have seen is you would see something on Stack Overflow, you just copy paste and you will try to change few values and try to do a trial and error on it. But please don't do that, because a lot of time I have seen that we end up wasting a lot of time and a lot of efforts, and if we don't understand what are the parameters of these functions are. I would recommend that Stack Overflow is good for getting the names, but once you know that, you would want to go to the documentation. Always go to the source of truth. So in this case, the source of truth is the OpenCV documentation, the docs.opencv.org. This is similar to those first principles. If you know the first principles, everything else becomes easy. Try to go to the source of truth over here. The source of truth is the OpenCV documentation. And if we go over here, I clicked on that. Now I see all the parameters that this function is taking. Now it becomes a matter of just understanding this and putting it in our program. The first one, again, there are two things over here. The first one over here is giving a void CV. So this is more of a C++ documentation over here. But we don't want that. We want the CV2 Python. Where is the Python documentation for this? We don't want to look at this because this is the C++ or the C version of it. The reason I found it was this is saying this is in the CV namespace. Well, that's not how Python uses it. I'm going to go back over here and try to look for the Python version of it. I'm going to say Python OpenCV CV2 dot rectangle and then try to look for documentation for that. So we have the line. Let's search for the rectangle. There are too many rectangles over here, but yeah, here it is. The Python version says, here's the Python version. There is C++ versions, and then you have the cv2.rectangle for Python. And over here, what we are saying is you give it the image, then the point 1, where do you want to start the rectangle from, the point 2, then the color, and then the thickness. The color needs to be rectangle color or brightness of the grayscale image. But again, they don't have it over here, but let me tell you that it's a tuple of the BGR values. The way we're going to do this is we're going to say cv2.rectangle and we're going to say input image. And then what we want to say is the start point. Let's say we start from 0, 0. And then what we say is, where do you want this rectangle to stop? Make sure that this tuple is less than the size of the image. In our case, the image was at least 200 pixels wide. So I'm going to draw a rectangle of 200 pixels. And then I want to say the color values. Let's say I want to draw a red rectangle. In this case, it's not RGB, but the way they have set it up as BGR, which is not very helpful sometimes because I tend to get confused with that. Make sure you give the values in BGR. I'm saying that it's 0, 0, 255. I'm drawing a red rectangle and let's give it the line width of 2. This is how it is set up. And let's draw this. Again, what you want to do is we are showing this image before we draw the rectangle. We don't want to do that. Let's take this line of cv2.show below this. Now we will see that on our screen as well. And maybe, you know what, you can take this one as well. Maybe we'll write to our screen as well. And I'm just using these extra line breaks over here to make sure that you guys see every line clearly, but it's not generally that a good practice. I'm gonna run this. As you see, we drew a rectangle over here, but we drew a red rectangle, but for some reason we are getting a black and white. The reason is we don't have the color information and we are storing that in just the grayscale image. Instead of having the 0 over here, if you remove that, now you will see that you're drawing a red rectangle on the screen. The next thing that we want to do is, let me give you an image that we would want to work with, and I would want you to download that image. I'm gonna paste this on the chat window. What we have is a image from a newspaper cutout of a Sudoku game. And what we want to do is, let's say we wanted a robot to learn the Sudoku from the newspapers. Not just a robot, but any computer vision algorithm. Now we want to train our machine learning algorithm to be able to read all the newspaper cutouts and then be able to understand how the game of Sudoku works. Well, in that case, it becomes really difficult for us to directly give this image to a machine learning model. Can you guys think of what is off in this image? Why is it so difficult? And why wouldn't you give this directly to a machine learning algorithm? It is tilted. Yeah, most importantly, it has a lot of redundant information. Not only in terms of these extra text that you see, think of in terms of the lighting levels over here. We have different grayscales. There is some shadow over here. All your machine learning model, it doesn't know that. It's going to take all of that information as well, and it's going to create the noise in that model. What you would rather want to do is be able to extract particular features from this image and be able to convert that into a format which is more suitable for a machine learning algorithm to work with. What we're going to do in next few minutes is try to convert this image to a better value. My question to you is, do you think that we should keep this image and give it as a grayscale image to a machine learning model or as a black and white image? And why do you say so? So let me try to explain it in a different way maybe. What we're trying to do is try to work with as much most relevant information as we can. We don't want to give a machine learning model something which is not important. In this case, there is a lot of extra information, not only in terms of the extra text that you see, but the visual information is also too much. There are some shadows over here. There are some tilts over here. The image is not formatted correctly for able to get the most relevant information. And over here, what is the most relevant information? The most relevant informations are these digits. We would rather have just these pixels, the boxes where we don't have these numbers and the boxes where we have these numbers as black and white images rather than trying to have a grayscale image, because the depth information is no longer useful. Grayscale images are generally useful if you are trying to deal with a 3D image. Let's say if I'm doing a face recognition or doing a hand gesture recognition, in those cases, maybe, you know what, the depth data might be useful. So I might use a grayscale image over there. But for an application like this, where we are just working with a 2D image of a picture, a 2D image of a Sudoku, we don't really want the grayscale image. We would just want to convert this to a black and white image. And the process by which you convert a grayscale or a color image to a black and white image is what we call as a thresholding. Name of the algorithm or name of the process is called as thresholding. Again, I have an example over here as well. What you would want to do is, if you have a grayscale image like this, let's say if you're trying to detect the number plates, or let's say if I'm trying to identify how many cars or how is the traffic right now on this street, I would want to get the number of cars. And to do that, there is a lot of redundant information. There is some street lights, there could be some pedestrians. I don't want all that information. I would want to convert this to a black and white image where the most relevant information is something which I preserve and I work with. Over here, I'm converting this grayscale image to a black and white image, and which has the most relevant information for me to work with. And this is how the histogram of a sample image would look like. In this case, for example, there are different grayscale levels. Over here, we have grayscale levels from 0 to 255. What our histogram is telling is how many number of white pixels are there in this image, how many number of black pixels are there in the image. What we are saying is there are some black pixels and there are some pixels which are more white. And what you could do is pick a threshold over here in between. If there is anything on the left of this threshold, I'll put that to 0 or I'll make it black. If there is anything to the right of this threshold, I'll make it a white. That is what we're trying to do over here. We're trying to have two discrete values. Instead of having from 0 to 255, if there are any pixels which are greater than this threshold, I'll round it up to 255. If there are any pixels less than a threshold, I'll round it up to 0. That is how you would go about thresholding an image or converting that image to a black and white image. Let's go ahead and try it out on our OpenCV program. What we want to do is convert this grayscale image that we have to a black and white image. Let's go over here. We don't want this I am right, so I'm just going to remove this I am right. We're going to push this I am show to the bottom, and we want to convert the image that we have to black and white. And again, I would want you to go ahead and find the name of the function which will help us to convert this image to black and white image. And then what we're going to do is go over and look at the parameters of that function. Maybe I can try to explain you what is going on in the magic that OpenCV is doing for us. So let me go ahead and try doing that. What I'm going to do is, here's how I would go about searching it. I'm going to go back to my Google and I'm going to say OpenCV, Python, and we want to do convert image to black and white. Let's say we go to our first Stack Overflow question. Again, we just want to use Stack Overflow as a reference. And then maybe we could look at the function parameters as well. Here's the most upvoted answer, and we know how to load a grayscale image, so that's good. But then if you want to convert that to a threshold, you want to convert that to binary image, or you want to convert it to black and white image, they've used the word binary over here, but it's same as black and white. Binary image is where you have only two values, 0 or 1. They have given us a good line over here along with what it means. It's clear that this is the threshold, this is the image black and white, this is the input grayscale image, and you could use two flags over here. We're gonna see what the flags are, but what you could do is directly let's go ahead and take this and first let's see if it works. And then what we could do is figure out what those things are. I'm going to copy this, paste it over here. And then what I want to see is CV2.threshold. We want to make sure that we give our input image over here, and we want to give it in a grayscale mode. So make sure that you use 0 over here. This will read it in grayscale itself. We are saying that the threshold over here is 128. What we are saying is anything less than 128, you keep it as 0. If anything is greater than 128, you make it 255. This is what we are saying over here. And then what we could do is use CV2.threshold binary. You could use either one of these. And again, these two are just flags. And what we could do also is just print them out on the screen and see what the values of these are. Most likely these are integers. Let me just go ahead and let's keep one of these and let's copy and print this as well. I'm gonna take this out and I'm gonna print on the screen what those two flags are, the values of those things are. I'm just gonna print both of these out on the screen. And the next thing that we want to do is we want to show this black and white image. So I'm gonna, instead of input image, I'm gonna show I am black and white. Save it, run this. And as you see, we got our black and white image over here. I should use the Sudoku file. Instead of image.jpg, I want to use sudoku.jpg. Let me make sure that I have it saved over here. I'm going to go to my sudoku.jpg, take it outside, put it in my folder. Make sure you use that. I'm going to use sudoku.jpg. And now let's run it. And we got the black and white image. It's not exactly what we were looking for, but we were able to convert that to our black and white image. And we also printed that those two variables over here. And as you saw, it's just two integers. You don't have to use CV2.threshold binary, the entire name every time. If you know that this value is 0, you could just write 0 over here. Those two are just two parameters, two integers, which is given to this function, which is telling it what kind of threshold to use. Over here, we are saying use the binary threshold, which will be 127 effectively. And this is another threshold option, which is based on another algorithm. Let's try using that as well. And let's see if what happens if you use 8 over here. How does that change? As you saw, this is a lot better than what we had before. We were still able to get most part of the image. It's not 100% clear and not exactly what we are looking for, but still better than what we were getting with the binary threshold. In this sense, there is a lot of back and forth and a lot of trial and error, definitely in image processing, because you would want to try out some different parameters and see what is working best in your application. So for us, you saw that the threshold, which was integer 8 over here, worked much better than having just the binary threshold. Again, here's what we are trying to do. We had this Sudoku image, which was a newspaper cutout. And it has a lot of irrelevant information that we don't want to give our machine learning model. The irrelevant information could be in terms of the extra text that is over here. It could be in terms of the grayscale levels which are over here, which don't really add meaning to what we are trying to do. Our end application is to maybe extract these digits and see what the value of this grid is. For an application like that, the grayscale value doesn't matter to us. What you're trying to do is convert this grayscale image to a black and white image. This process is called as thresholding, of converting a grayscale or color image to a black and white or a binary image. To do that, we went ahead and we saw that we went to OpenCV, we looked for a function to threshold that, and we got this function over here. And this function takes a few parameters. The first parameter is the input image. The second one is at what level do you want to do the threshold? Let's see over there, if you saw that there were a lot of things which were going black. What happens if I change 128 to 100? Does that improve things? That actually makes things even worse. Instead of 100, what if I do 140? Now we have still more white space over there. You could try out few values over there and try to see what is working best in your application. But over here, I'm going to say is 128 as my threshold level. Once you are done with this, we can try out some other stuff as well, some other type of thresholding, which is going to help us to get a better sense of the image. I also want you to think why this portion of this image that we are trying to do is going black, and we were still able to get reasonable results in this section, but this section we are just messing it up. Can you think about why is that happening? I have both the images, the original image and the converted image, right next to each other over here. Look at it and see what is going wrong in that section. Why aren't we getting that correctly? Yep, more than threshold is turning black in that region. The section is darker. There is definitely some shadow in this region which is causing it saturated to going towards the black levels. Instead of having just one fixed threshold for all the regions of the image, what if we had an algorithm which will look at an average value in this region and then try to threshold it? It will make our algorithm much more efficient. Instead of having one threshold of 128 throughout this image, what if we did an average of this region? Let's say if I take an average and the average levels, the gray level or the average gray level in this region is around, let's say 200. And then based on that, I decide my threshold. That will change things significantly, or that will help us significantly. And the way to do that in OpenCV is to use a thresholding method called as an adaptive threshold. Instead of just using a simple threshold, what we could do is use an adaptive threshold on our OpenCV image. Look for the function adaptive threshold and see what the parameters of that adaptive threshold are, and then maybe we can try it out. And let me know if that is not clear on why using an adaptive threshold will make our life better and how that works as well. Instead of just having one threshold, we would want to have a threshold which changes based on the average brightness level in that section of that image. The question is, why do we need to explicit threshold? The way this threshold function works is it returns two values. So you don't need to have these brackets, I'm assuming. Let me check if this works as well. And as you see, you don't need to have those brackets. What we are saying is this returns two values. The first one is the threshold which it is using, and the second one is the image. That's why we have two values over here. The way this function is written is it returns two values. So yeah, you can always try changing the threshold levels and try to see what happens. For the parameters over here, we have only two values. Let's go and look at the documentation of cv2.threshold and it will be more clear over there. Let's say cv2.threshold Python. Let's look at the documentation. Let's go to the source of truth. And over here, as we see that you could have these 4 or 5 ways of doing it. So you could have threshold binary and all these other ways. Again, I want to make sure that this is Python. Yes, it is Python. You could have all these different variations of the binary thresholds. Try those things out and you would see different results based on the algorithms that they are using. And they have also given us an example of output. This is the binary threshold. You either have black or white. This is the inverted binary. Over here, they have more of a gradient function. So instead of just having black and white, you also have a gray scale almost. And then again, there are 2 different variations of this as well. And then you have the adaptive threshold over here as well. Let's say if I want a block size of 200 pixels. If you use a round number, it might not work, because generally the way the grids are set up in an image is you would want to have a 3x3 or 5x5 or 7x7. So it's generally an odd number. If you use an even number, it might show you an error. So try using an odd number for the block size over there. Let's go ahead and try it out. What I'm going to do is go back over here and look at an example over here. This is the same example that we are working on. We tried the global thresholding and it gave us this result, something similar to this. What we're trying to do is try to do the adaptive thresholding. Let's take this example over here and let's copy this and try it out on our image. We are going to take this, make sure they are using CV, make sure you use CV2. I'm going to take CV2. Instead of image, I'm going to say input image. The maximum level is 255. Then we are going to say use the adaptive threshold mean. There are 2 variations to this. We could use either one. You could either use adaptive threshold mean or you could use the adaptive threshold Gaussian. Don't worry too much about those, but again, those are just two variations of how you could go about doing those averages. And then let's keep the default values of these and we can try changing these and see what happens with our image if we try different numbers over there. there is definitely some trial and error in there, and you'll have to figure out for your application what are the values which are working best. Sometimes you get a guidance from our online community on what are the values, the range of values that you should use. But in some other cases, you would have to figure it out yourself by doing some trial and error. Let's try this out. Instead of I'm black and white, I'm going to do the TH2, which is the threshold to image. And I'm going to save it. We don't want this first one. So let's just comment this out so that we don't get confused. And there is some error because we are not saving CV2. Make sure you use CV2 over there, CV2, and this is CV2 as well. And we get a much better result. Instead of just having those things over there, the entire black region just went away. And maybe we can try out some other values over there as well and see what happens in our application. What I'm also gonna do is also try out some other values of these two parameters that they have given us. Let's say instead of 11 and 2, let's try 5 and 7 and see what happens. What we are saying is this is the block size over here, right? So instead of having an average around 11, I'm gonna reduce my block size and see what's gonna happen. And as you saw, for our case, this value worked much more better than what we had before. Instead of just copying and pasting from the internet that we just saw, what we did was try to change those values of those numbers so that we get a much better result. But now, as you see, once we have done this, it makes our life so much easy to feed it to a machine learning algorithm. The most relevant information is now. We have it in our hand and we can process it further to maybe identify the digits, or maybe if you want to convert it to a grid or a matrix, now all of that becomes possible. That was it for our today's session. And thank you so much for joining in. I hope you guys learned something today and something that was interesting. I hope that a lot of you will join us again for our next session as well. And before you go, I would want to make sure that you leave some comments on our Facebook page. Please go ahead and send us some reviews. It's really something that drives us. That's the only form of feedback that I have. And it might be just a few seconds for you to go and drop some reviews for us. But I can't tell you how important that is for us to keep doing the workshops like these. It might just take few seconds for you, but it means a whole lot of things to us. Thank you everyone once again. Even though some of it might have sounded like magic and we were doing a lot of copy pasting from internet as well, but that's how you get started in a new field. You want to make sure that you learn to crawl first before you start running. So this is what we were doing. We were trying to crawl from the stuff that was already available on internet. We tried to take those things, try to run it, get our hands dirty with it before we try to do something of our own. The next webinar, so we generally try to do it every weekend. If you look on our website, if you go to codeheroku.com and log into your dashboard, on that you would see a timeline. Right now we don't have any new workshops scheduled yet, but by Wednesday or Thursday you would see the new workshops which are scheduled for the next weekend. All the resources, the recorded videos, the code that you saw, everything is going to be on our Facebook page and on our YouTube channel as well, and also definitely on our website. Thanks once again for attending. If you have any questions, feel free to email me anytime. I'm generally responsive on our Facebook page as well. So if you drop me a message over on the Facebook page, it's most likely that you're going to hear back within few hours at most. Or you could always email us as well. And our email ID is hello@codeheroku.com.